Hello there, I'm Bryce Adelstein Lelbach. I'm thrilled to be here at C++ Now 2021 to talk about a topic that's been on my mind a lot recently: what belongs in the C++ standard library. Today, I'm the chair of the C++ Committee's Library Evolution Group and the US Programming Languages Committee. I work at NVIDIA, where I lead our strategy for HPC programming models, C++ compilers, and C++ libraries. 10 years ago, I spoke at this conference for the first time, back when it was called BoostCon. It was the first conference that I ever attended. I was 19 years old at the time. A few months earlier, I had discovered programming and taught myself C++. It was an obsession. I knew then that I'd be doing this for the rest of my life. Soon after that, I started contributing to Boost. At the time, that seemed more important than school, so I dropped out of college. Well, technically they kicked me out because I stopped showing up to classes. This was not a smart decision. It made my career path a lot harder. But I was fortunate enough to find people willing to help me and take a chance on me. I needed a job, so on a whim, I reached out on IRC to Hartmut Kaiser, a Boost maintainer I worked with, to see if he knew of anyone who might hire me. He told me that I should come down to Louisiana State University and work in his research group. My parents thought it was a scam or something worse, but I took him up on the offer and I bought a one-way ticket to Baton Rouge. It was Hartmut who encouraged me to speak at BoostCon 2011, and I'm glad he did because it absolutely changed my life and set me down the path that I'm on today. For the first time, I was surrounded by people who appreciated and understood me and my passion for software. I felt welcomed, I felt like I belonged, and I met people who have become some of my closest friends. I was fortunate that I found a job and mentor who encouraged me to get involved in my tech community and paid for me to attend conferences. But I knew there were people out there like me who weren't so fortunate, who hadn't found their way yet. So when John Kalb announced his vision for C++ Now and asked for someone to organize its student volunteer program, which would give people scholarships to attend the conference, I eagerly said I'd do it. My first experience at a tech conference transformed my life. I wanted to help bring that experience to others. I wanted to find people who hadn't been discovered and give them the same opportunities that I had been given. Over the years, the student volunteer program has brought some amazing people into the C++ community. Many of our alumni are members of the C++ committee, speak regularly at C++ conferences, and work on critical C++ projects that we all use. I believe the C++ Now student volunteer program is the most important thing I've done in the past decade. I'm incredibly proud of the program and all the people who have passed through it. This is a talk about what belongs in the C++ standard library. But before we get to that question, I want to address a more important one. Who belongs in the C++ community? I want everyone to feel as welcome in the C++ community as I do, to feel like they belong here. We've made great strides towards that goal over the past decade, but we still have a long ways to go. Our community is not as inclusive as it could or should be. As a leader in the C++ community, I feel it is important to acknowledge that we have a diversity and inclusion problem. The first step in fixing a problem is recognizing it. The next step is to organize and take action. And that's why I'm glad that we now have Include C++, an organization dedicated to making our community more welcoming, inclusive, and diverse. After I volunteered to run the C++ Now student volunteer program, I started volunteering to do other things. C++ Now program chair, CPPCon program chair. Eventually, I joined the C++ committee. After a while, I started volunteering to do things there as well. Library incubator chair, tooling chair, and finally, library evolution chair. Library Evolution is the subgroup of the C++ committee that is responsible for the roadmap of the C++ standard library. Library Evolution decides what new features or changes to the C++ standard library should be pursued, selecting from proposals developed by domain-specific study groups and the Library Incubator Group. Library Evolution selects and develops a design for those features and changes, and then hands them off to the core library group, where the design is validated and a specification is produced. My role as Library Evolution Chair often has me thinking about the question that we're going to discuss today. What belongs in the C++ standard library? First, I think we need to talk about what has made C++ successful as a programming language. Is it performance? Performance is certainly a part of C++'s success. We definitely aim to leave no room for a faster language than C++. One of the core tenets of C++ is the zero-cost abstraction principle. You shouldn't pay for something you don't use. But there are other fast languages. Why not use Fortran, or Rust, or C? Performance alone is not what makes C++ successful. What about portability? That's supposed to be one of our key selling points, right? C++ runs anywhere. But for all its portability, doesn't C++ have a lot of non-portability? All that implementation defined and undefined behavior? If we really want portability, maybe we should use Java or some JVM-based language. Portability alone is not what makes C++ successful. What about stability? That's a defining part of C++. I mean, it's a language that took another language, C, as its starting point. And stability certainly influences C++ evolution, as we'll discuss today. But many other languages have stability. If that's all you want, why not use COBOL? Stability alone is not what makes C++ successful. I think the thing that's made C++ successful is something I call universality. C++ can be used to solve any class of problem, using any programming paradigm or technique, on any platform. For certain problems, for certain paradigms, for certain platforms, there may be a better but less flexible solution. But with C++, you have one language and one ecosystem that can be used for almost anything. C++ is fundamentally a multi-purpose and multi-platform language. This flexibility and diversity is the key to C++'s success. But as we'll learn, it's often one of the main things that limits how we can evolve C++. There are over 5 million C++ programmers in the world and billions of lines of C++ code running all over this planet and on a few others as well. It's almost impossible for any of us individually to comprehend the full scope of how and where C++ is used. We each have our own individual view of what the world of software development looks like, a view usually grounded in our personal experiences in the domains that we've worked in. Based on that worldview, we all have ideas about how C++ should evolve and what the C++ committee should prioritize. Those ideas often seem obvious to us, so we wonder why the C++ committee doesn't do them. Maybe they're just out of touch? But it is not that simple. Each person and each domain has a different, often conflicting idea of what the C++ committee should be focusing on. We cannot just consider the needs of one specific group of users or platforms in isolation. It's not an efficient use of our time. We must try to build features and abstractions that are as close to universal as possible. Many of us need to develop what I call use case sympathy. We need to learn to accept the importance and validity of use cases that we are not personally familiar with or believe in. If you only care about what matters to your domain or platform, you will be wildly unsuccessful on the C++ committee, because our mission is to serve all users. The C++ committee has to seek solutions that will be acceptable and useful to most of our users and implementable on most of our platforms. That's a very narrow space for us to work in. Often, we ask, is the portable subset of this functionality that we can standardize enough to actually be useful? The answer is no more frequently than I'd like. Greater universality takes greater effort. As the number of use cases we try to make a feature support grows, the effort to standardize grows exponentially. We want to try to avoid this space on the right here. Trying to satisfy all 5 million C++ programmers is hard, and in many cases impossible. But we also want to avoid this space on the left. Standardizing features that only satisfy one group of users isn't a good use of our time, especially if it's a feature that could support a much broader user base with a bit more work. We also want to avoid serving some of our users at the cost of others. If we build a feature that two groups of users want, but that only serves the needs of one group, we risk increasing the fragmentation of the C++ ecosystem. We generally want to try to be in this green space in the middle here. We want to standardize features that support many use cases across multiple domains and platforms. But we can't satisfy everyone, so we should make sure we clearly define what's in scope. One of the keys to success in C++ evolution is incrementalism. Often, the first release of a feature will have a more limited scope, but will leave room to expand and build upon it in future releases. I can't think of a single major C++ feature that we haven't substantially extended in later releases. Take constexpr, for example, which has evolved a lot from C++ 11 to C++ 20, and will probably evolve more in the next decade. Let's look at an example. Should everything in the C++ standard library support allocators? For some people and domains, controlling allocation is absolutely essential. In some environments, C++'s default allocation methods, new and std allocator, simply won't work, and it's important for users to be able to customize how allocation is performed. For example, if you're writing an operating system or device driver. Alternatively, if you're in a real-time or safety-critical environment, all your allocations need to be deterministic, which would require a custom allocator. Also, some consider allocation to be fundamental for performance. They must use a memory pool or stack allocations to be able to meet their performance requirements. There are also many people who need to work with special kinds of memory. The C++ standard has a flat, uniform view of memory, but in reality, there's many different kinds of memories that you may need to deal with. For example, shared memory for inter-process communication, memory mapped I/O to talk to hardware, or GPU memory. But it seems like it's straightforward to make most things support allocators, right? std vector, for example. I bet most of us would agree that it's quite reasonable for std vector to support allocators. We'd probably also agree that most of the standard library containers should support allocators, yeah? But there's actually a lot more complexity here than you might think. Do we make containers support stateful allocators? If so, then what happens when you copy assign, move assign, or swap a container? Do you propagate the allocator? In some cases, you'll want to propagate. In other cases, you won't. So now the standard library needs a way for users to customize that behavior. What about other vocabulary types like tuple, pair, and optional? Do they need to be allocator aware? Those types don't even allocate or manage memory themselves, but the things that they contain might. Do we have to think about allocator support for every facility that might contain a user-defined type? What about type erasure facilities, which will have to type erase the allocator under the hood? It turns out that this is actually quite challenging to do correctly. How do we recover the type erased allocator when we need it? How does allocator propagation work? If the type erased allocator doesn't propagate on move assignment, but the type erased allocator on the right-hand side of the assignment does propagate on move, what do you do? std function originally had support for allocators, but it was so broken that we had to take it out in C++ 17. What about std generator, which we're trying to get into C++ 23? If it supports allocators, do we always type erase them? How will allocators work with nested generators? How much effort are we willing to spend on this? How much longer will std generator take to ship if we add allocator support? Supporting allocators everywhere has a cost. And that brings up another example. Should everything in std have a type erased form? Type erasure is important for some users, while others want to avoid it at all costs. Type erased facilities can be critical when you have generic code that you don't want to expose as templates in a header and instead want to encapsulate in a source file. You might want to do this to reduce build times, for example. Type erasure is also important if you're dealing with dynamic input, interfacing to dynamic programming languages, or supporting plugins. But type erasure does come with overheads, indirection and dynamic memory allocation. We have type erased facilities for invocables, std function and the new std move only function, and we have type erased facilities for allocators, std PMR. But do we need a type erasing wrapper for every concept in the standard library? Should we have type erased ranges instead? How about type erased iterators instead? Where do we draw the line? C++ standardization often moves slower than we'd all like because it is incredibly challenging to decide what's in scope and find solutions that'll work for most of our broad user base. You might be wondering if perhaps that means we should prioritize some users over others. In some cases, we do that. If we believe a use case is very uncommon or fringe, it's not as important to us. But if we start prioritizing large groups of users over other large groups of users, we risk fragmenting the entire C++ ecosystem. Universality is a double-edged sword. The breadth of C++'s ecosystem is our greatest strength, but it's also our greatest weakness. We can't just stop caring about or de-scope large swaths of our ecosystem. The breadth of that ecosystem is what has made C++ successful. If we're not serving all our users, then what's the point? And to be clear, we're not serving all of our users as well as we should be today. There are many parts of the C++ community that avoid the C++ standard library entirely for one reason or another. If anything, we need to increase the scope, support more use cases, not fewer. This is a talk about the C++ standard library, but what is the C++ standard library? Often, we conflate C++ standard library implementations with the C++ standard library itself. GCC's libstdc++, MSVC's STL, LLVM's libc++, and NVIDIA's libnv++ are not the C++ standard library. They are C++ standard library implementations. The C++ standard library is a specification. There are multiple implementations of that specification. That makes the C++ standard library an inefficient vehicle for delivering features. Implementation effort is duplicated by each major vendor. When you develop a feature for a C++ library, there's just one code base and one implementation. Most of that code will probably be platform agnostic. There will probably be some code that is specific to a particular compiler, operating system, or hardware architecture, but for most projects, that will be only a small portion of your code, and it will be neatly encapsulated. The C++ standard library is different. When we add a feature to the C++ standard library, LLVM will have to do one implementation. GCC will have to do one implementation. MSVC will have to do one implementation. When we consider whether we should add something to the C++ standard library, we must ask ourselves, is this inefficiency going to be valuable? Will we gain any benefit from multiple implementations? Is there a different optimal implementation for each platform? The C++ standard is descriptive, not prescriptive. It does not prescribe exactly how everything is implemented. It describes the structure of C++ source code, the semantics of the abstract machine that executes said source code, and requirements on how that abstract machine is implemented. The standard specifies enough to be portable and consistent across platforms, but the standard also grants enough freedom for each platform to choose the right design for their implementation and environment. We call this implementation freedom. It's essential to standard C++. I think many people don't appreciate the value of this. If we tried to specify everything and didn't leave room for implementation freedom, C++ would be less portable, not more portable. C++ would be less performant and it would be less flexible. There'd be fewer platforms that could even implement C++. Implementation-defined and undefined behavior are often a feature, not a bug. Consider std mutex. There's many different options for how std mutex can be implemented, and your implementation can pick the best option for your platform. If you're running in an environment with an operating system, an OS kernel mutex or futex can be used, which will be fair and perform pretty well under contention. If you're running in an embedded environment or without an operating system, your implementation can implement std mutex with a spin lock. On a microcontroller with only a single thread, std mutex can be implemented without any synchronization, just disabling interrupts. Another example would be the indexing operator on random access containers in the standard library. Some people would like these operations to require bounds checking, but not everyone wants that, and it comes with a performance penalty. So other people would like a guarantee that these operations never bounds check and never throw. The C++ standard library doesn't just pick one of these options. We neither require bounds checking for these operations, nor explicitly forbid an implementation that does bounds checking. Implementation freedom means vendors can give us the right C++ for our environment. If you're debugging your code, use a debug version of your standard library, where container element access and iterators will be checked. When you need absolute maximum performance, you can use a different, unchecked production version. The C++ standard's more what you'd call guidelines than actual rules. It's descriptive, not prescriptive. It grants a great deal of implementation freedom, and that's a good thing. Standardization takes time. Half of the C++ community thinks that the C++ committee moves too slowly and isn't adding enough things. The other half thinks we're moving too quickly and adding too many things. Other C++ libraries can define a narrower scope than the C++ standard library. They don't have to try to support every platform and all 5 million C++ programmers. They can choose to target specific platforms. They can focus on specific domains. They can have shorter lifetimes and roadmaps. They don't have to plan where they'll be in a decade or 2 decades. That focus gives you agility. Other C++ libraries can be quickly developed and distributed. This wasn't always the case, but today it's easy to publish a library on GitHub or with VC Package or Conan. The C++ standard library does not have that luxury. We can't just say, sorry, this feature isn't supported on Windows. We can't focus on just one group of users or one domain. We build universal and widely applicable facilities. It takes time for a standard feature to become widely available to most C++ programmers. If you're watching this video, you're likely someone who tends to use the latest C++ standard dialect when you can. But that's not the case for the majority of C++ users. It's only now, in 2021, that C++11 is truly reaching full deployment across the C++ ecosystem. What we standardize must stand the test of time. If it takes a long time to develop, deploy, and get it adopted, we better take the time to make sure we do a good job, because it'll take just as long to fix any mistakes we make. I think on the scale of decades. Where does C++ need to be in 2030? In 2040? I think that way because that's when the work that I'll be doing in 2021 will become widely available. Standardization is slow and hard, but it has one redeeming quality. When it is finally deployed and widely available, it can have a huge impact because it's everywhere. But for many things, the time and effort required for standardization probably isn't worth it. You may be better served with a C++ library with a narrower focus and greater agility that you can just get from GitHub. And often, for something domain-specific, you're going to be much better served by a C++ library provided by and focused on that domain, instead of something in the C++ standard library. It's important to understand that C++ standard library implementers aren't domain experts, And the people who are domain experts often don't have the experience to understand the onerous requirements on C++ standard library implementations and the scale of C++ standard library deployment and distribution. As a C++ standard library implementer, I often feel I lack the expertise to build some of the domain-specific things that are in the C++ standard library. A few weeks ago, I got asked if my team could implement some of the C++ mathematical special functions in the NVIDIA C++ standard library. And I told them our team is not equipped to do that. We don't know how to implement and test a spherical vessel function. Fortunately, there's some great folks at NVIDIA who do have those skills, and we can work with them to make it happen. But that's not always the case. Sometimes you end up with a C++ standard library implementer working with stuff way outside of their comfort zone. Now, C++ standard library implementers are some of the smartest people I know, and they're very adaptable. But that does not mean that they are the best equipped person to build a domain-specific feature. A great example of where this has led to problems is std-regex. Std-regex implementations are slow. And it's not solely problems with the design of the interface. The std-regex interface was based on boost-regex, but boost-regex outperforms std-regex implementations in most cases. It's mostly quality of implementation. Building an optimized regular expression framework is a full-time job, and implementers have an entire C++ standard library to take care of. They can't just spend all their time optimizing std-regex. Implementers are experts at their specific platform, balancing trade-offs across a diverse user base, and handling corner cases that no one else would think of. But they're not the people best suited to do very domain-specific work like mathematical special functions, std-regex, or carconv. Now we've reached the epic conflict at the center of this talk, the fight between good and evil. Stability versus velocity, locked in a struggle from which only one can emerge victorious. It's actually a lot more nuanced than that. We're going to get into it. Let's start off with a very simple principle, which, sadly, the C++ standard library falls victim to. Hiram's Law. With a sufficient number of users, it doesn't matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. This makes it quite difficult for us to change things in the standard library after we've shipped them without breaking people. Here's a great example from the field. MSVC was unable to roll out a change to their std string destructor because a user depended on being able to destroy the same string twice, and for whatever reason it wasn't okay to break said user. Every observable aspect of a C++ standard library implementation becomes part of its interface. There's two different components of the C++ standard library interface. The first is the API, the syntax and semantics of the interface and source code. This is defined by the C++ standard. The second is the ABI, the binary representation and conventions for machine code compiled from that source code. This is not explicitly specified by the C++ standard, but it is derived from the standard, and it does influence the evolution of C++. C++ language ABI is the binary representation and conventions for C++ language facilities on a particular platform. For some platforms, there's a separate specification that defines the details of this ABI. For example, many compilers on x86 and ARM POSIX platforms conform to the Itanium C++ ABI. C++ language ABI includes things like function calling conventions, what registers need to be saved, how parameters are passed, and where return values are stored. Name mangling, how C++ names get encoded into symbol names that are used in object files and binary artifacts. The layout, size, and alignment of types. The layout of virtual tables and the conventions for making virtual function calls. How exception handling is implemented. And how floating point math operations are performed. These are just a few examples of what a C++ language ABI covers. C++ language ABIs tend to be more rigid and harder to change. Changing them tends to have much broader impacts on tools, on other languages, on kernels, and on operating systems. C++ standard library ABI is the representation of the facilities in a specific C++ standard library implementation under a particular C++ language ABI. A standard library ABI is separate but derived from the underlying language ABI in use. Among other things, C++ standard library ABI includes the linkage of std functions. For example, std memcopy. Is it extern C? Does it have the same address as C's memcopy? The mangling of std types and functions. Is an inline namespace used for std? Are overload sets implemented with distinct overloads, or functions with default parameters? The layout, size, and alignment of std types. What is actually contained in a std string? Is there extra space for a small string buffer? If so, how much? The virtual tables for polymorphic std classes, such as IO streams. Also, any virtual tables or similar mechanisms used to implement type-erased std facilities, like std function. Perhaps surprisingly, even context where values and functions in std can be considered part of a C++ standard library's ABI. For example, std dynamic extent is the default parameter of std span, which means that its value is part of the mangled name of std span. Likewise, anything in std that can be evaluated at context per time, such as type traits or concepts, are part of standard library ABI. Context per evaluations of such facilities can influence return types, overload sets, and the layout of types. Today, our focus is on the C++ standard library, not the core language. For the rest of this talk, when I say ABI, I'll be referring to C++ standard library ABI. When we say stability, what exactly do we mean? API stability is the philosophy that existing syntax and semantics should rarely change. I think most in the C++ community would agree that changing existing syntax and semantics can cause pain for users, and thus we should take caution when making such changes. That said, I think many, including myself, would like a way for C++ to move beyond some of its legacy syntax and semantics, especially those that we adopted from C. ABI stability is the philosophy that binary representations of existing facilities should rarely change. I don't think there's agreement in the C++ community about the importance of preserving the binary representation of existing facilities. A number of people question the validity of the use cases for ABI stability. This is a good example of a place where I think we often lack use case sympathy. Stability is linked to the idea of compatibility. In the context of this discussion, backward compatibility is when a newer compiler or language dialect supports building older source code. For example, imagine we've got a component A which depends on another component B. Both were written as C++11. If we have backward compatibility, then compiling them for C++23 will work. Compatibility gets more complicated when you start thinking about dependencies and mixing code compiled with different toolchains, versions, and language dialects. Imagine that we want to compile A as C++23, but we want to use a build of B that was compiled as C++11. Maybe B was even compiled with an older toolchain. Or perhaps we have some new code, C, that was written for C++23 but depends on a component D which is compiled as C++11. The expectation that an older build will support newer code is forward compatibility. Forward compatibility is when code built with an older compiler or language dialect can be used by newer code compiled with a newer compiler or language dialect. One of the motivations of forward compatibility is dealing with dependencies, especially those that are external to your project. Users don't always have the option to rebuild dependencies. Sometimes they don't have access to the source code. Sometimes the dependencies can't be built with the newer dialect or compiler. Sometimes moving to a newer build of the dependency can have a cascading effect. If you want to use a newer build of your C++ standard library, you might need to use a newer build of your C standard library. And on some platforms, that may mean that you have to upgrade your kernel or operating system. So how could this problem be addressed today? You could expect your dependencies to distribute multiple versions, each of which can be used in isolation. Imagine I've got a codebase X, which depends on the standard library. There's another codebase Y, which also depends on the standard library. Unfortunately, Y is using an older C++ language dialect than X. The standard library implementers could distribute two versions, one for X and one for Y. Windows did this for years. It's a bit harder to do it on POSIX. The problem is that you can't have X and Y pass any standard library objects between each other. You'd end up with one definition rule violations and general mayhem. That's a tough constraint to live with because a large part of the C++ standard library's purpose is to provide common types that libraries can pass between each other. Now, one way you could avoid that problem is by writing your ABI stable interfaces in C, because C has a much smaller ABI surface. But, ew. I mean, this is C++ now. Just use C is probably not the solution you're looking for if you're watching this video. You could also build and distribute all your dependencies yourself. This might make sense for typical dependencies, but you probably don't want to be compiling and distributing your own build of your C++ standard library, as it's tightly coupled to whatever C++ compiler you're using. If you can build the whole world yourself, this is a good approach. It can let you live at head for everything, which is really valuable, but it's not an option for everyone. Many people don't have use case sympathy for mixing older builds and newer builds. Some take the position that mixing code compiled with different C++ dialects shouldn't be supported. One solution that is often suggested for such users is for them to just not upgrade to a newer C++ dialect if they can't get newer builds of all their dependencies. In some cases, I think this is quite reasonable guidance. However, there's a big downside to this, which I think may make it self-defeating. Suppose we forbid mixing builds from different C++ dialects. That's going to make it harder for a project to move to new C++ dialects. They'll have to wait for all their dependencies to move. That means all the things that depend on that project will take longer to move to new C++ dialects. And that will turn into a vicious cycle. It's a viral adoption problem. Either everyone adopts or no one does. How many years did the Python 2 to Python 3 migration take? Do we want to have to deal with something like that? I'm sure many of you have had to deal with some ancient tool chains for far longer than you'd like. I remember fixing MSVC 2005 bugs in 2018. If we make breaking changes to C++, we might make it a lot better, but how long would it take to get adopted? When we're considering making a breaking change, one of the key questions is how will the break manifest? Will it break at build time? If so, does it happen at compile time when we can give a good diagnostic? Or at link time when we don't have semantic information? If it can't be caught at compile time, how does it break at runtime? Can it be made to fail gracefully? Can we diagnose the problem and report an error? Or will it fail catastrophically? If so, how catastrophically? Will it cause crashes, buffer overflows, silent data corruption? Does it fail consistently? How reliably can it be diagnosed, either at compile time or at runtime? Can we catch all cases, or at least most of them? We prefer that breaking changes happen at build time and can always be diagnosed. In some ways, breaking changes that fail to compile are more disruptive, but we're more willing to accept them because they prevent you from shipping broken code. For API breaking changes, all of this is straightforward, at least compared to ABI breaking changes, which are often more subtle and far more complex. It's not always obvious when something is an ABI breaking change. So let me show you some of the ways that ABI changes in the C++ standard library can manifest and break your code. Using standard library types in your library interfaces will expose you to ABI breaks. Let's imagine that the layout of std_string changes in our C++ standard library between C++ 11 and C++ 23 for some reason. For example, maybe we decide to mandate that std_string must have a buffer to store smaller strings that will fit without requiring an allocation, and in our C++ 11 implementation, we have no such buffer. Now I've got a problem. I had one definition of std_string with one layout and size when I compiled the function f as C++11. I've got a different definition of std_string with a different layout and size when I compiled g as C++23. This is a violation of C++'s one definition rule. This won't be caught at compile time, and you're going to have a bad time at runtime. Suppose the std_string we constructed in G is small enough to fit into our small string buffer. But when f was compiled, there was no small string buffer, so it doesn't know to look for the string contents there. If we're lucky, this will cause the code to crash at runtime. If we're unlucky, it'll just read or corrupt some other memory. Likewise, if we return std types from functions, we can end up with the same type of problems if the C++ standard library ABI changes. Having std data members in our own types can lead to ABI breaks too. These can be harder to notice and detect because the dependence on the std ABI may not be syntactically visible. All we see is our types being passed around. What if we have a function that uses std_string internally, but not in the interface? Is that fine? If we're linking against our standard library's shared library binary, we might think that we'll be ABI resilient if the size and alignment of std_string doesn't change. If the layout changes, but the size stays the same, we should be good because we'll be calling the member functions in the shared library, which know about the new layout. That's okay, right? Yeah, not exactly. What if some of those member functions are defined in our standard library's headers and they got inlined into this function, while others are defined in the standard library binary? If we're linked against a newer standard library with a different definition of std_string, then we're in trouble because we again have conflicting definitions. The std_string member functions in the shared library have a newer definition, and the std_string member functions inlined into our code have an older definition. Again, we have an ODR violation and mayhem. If you use const for values from the C++ standard library, you're exposed to std ABI breaks too. Imagine that an implementation wanted to change their value of std hardware destructive interference size, which is often used to align atomics so they won't conflict. Such a change would cause the layout and size of my ticket mutex here to change. It may not even be apparent that you're using const for std values in your code. For example, std span has a second template parameter which is defaulted to std dynamic extent, a const for std size t. What would happen if we changed the value of std dynamic extent? That would cause the mangled name of std span to change, which would cause the mangled name of any functions that take a std span to change. So if I had a function compiled with an older definition of std span and I tried to call it, I'd get a link error. The compiler wouldn't be able to find the function because the old mangled name wouldn't match what was expected. Similarly, if we changed std span's second parameter to be a template auto parameter and replaced std dynamic extent with a value that's a tag type, that would change how std span is mangled, causing an ABI break for anyone downstream. Likewise, a change to anything in std that can be evaluated at const per time can lead to ABI changes in your code because those evaluations can affect types and signatures. For example, you might use metaprogramming with a concept or type trait to compute a type, or you might use concepts or type traits to constrain an overload set. Changing anything in std that can be evaluated at compile time can end up breaking the ABI of users' code. Polymorphism and type erasure in the standard library exposes you to ABI breaks in a variety of different ways. If we ever remove a virtual function from a polymorphic std class, that will change the virtual table, which will cause layout changes. Even worse, adding new virtual functions to a polymorphic class in std will change the virtual table layout. In most cases, we can add functionality to facilities while preserving ABI. For polymorphism, type erasure, and named concepts, adding functionality usually breaks ABI. C++ standard library polymorphism, type erasure, and named concepts are like diamonds. They're forever, and they're hard to change. This is a big problem because typically we develop features incrementally. We try to release a minimal viable product first, then add on to it later. It is usually impossible, or at least significantly harder, to do that for std features that use these techniques. For me, that means the bar is much higher for a feature that uses polymorphism, type erasure, or named concepts, because I know that we're going to be unable to extend or improve that feature later. Now, let's take a look at some historical examples of how ABI constraints and breaks have impacted C++ standard library evolution. For C++11, std list size could be implemented with linear time complexity, which meant that implementations did not need to store the size of the list as a data member. They could just walk the list when they needed to determine the size. In C++11, we added a requirement that std list size have constant time complexity, which meant that std list implementations now had to have a size member. For implementations that previously didn't have a size data member in their lists, such as GCC's libstd C++, this was an ABI break. Adding a size data member would change the layout of their std list and increase its size. Before C++11, some implementations, like GCC's libstd C++, implemented stdstring with copy-on-write semantics. Each stdstring was a cheap type that held a pointer to some internal string representation object. That object would hold the size, capacity, and a pointer to the actual string, which would typically be dynamically allocated. When you copied a string, the copy would point to the same string representation. This made copying stdstring cheap. When you modified a stdstring's contents, if any other strings pointed to the same string representation as that string, it would make a copy of the string representation and modify the copy. This had some performance advantages, but it could also introduce performance problems as it introduced an additional level of indirection. This implementation strategy also caused several problems relating to object lifetimes. You could get into situations where your std strings would end up with pointers to string representations that were no longer valid. The biggest problem was not copy-on-write itself, but the fact that not all implementations used this strategy, so you'd get different semantics and performance with different C++ standard library implementations. In C++11, we effectively prohibited copy-on-write implementations of stdstring by adding a number of new requirements to it. Implementations that used copy-on-write had to switch to a different model. Stdstring had to be implemented like a std vector. Each stdstring had to own its own contents. This made stdstring semantics more consistent and prevented a number of odd quirks that copy-on-write caused. This was not necessarily a performance regression either. It was more of a trade-off. Implementations could do a small string optimization where they'd put a small buffer into their stdstring. If the stdstring's contents were small enough to fit into the buffer, they'd put it there and avoid doing a dynamic memory allocation. Otherwise, they'd use the buffer to store the capacity and a pointer to the dynamically allocated string. Typically, this buffer would be at least 16 bytes, the size of a size t for the capacity and a pointer, which would be what you'd need if the string was large enough to need a dynamic allocation. I believe the C++ 11 std list size complexity change, and especially the stdstring copy-on-write prohibition, were the right moves for C++. However, when the C++ committee made those decisions, we didn't comprehend the scope of the impact this would have on the ecosystem. Stdstring is used everywhere. Changing it broke a massive amount of code and caused an immeasurable amount of suffering. Diagnosing and fixing these breaks when using GCC's libstd C++ was a pain. I know some folks who are still dealing with those issues today. I believe that these ABI breaks significantly slowed down the adoption of C++11. In C++11, std lockguard took a single template parameter, the mutex type which it would lock. Locking multiple mutexes with std lockguards was complicated and error-prone. If you just tried to construct two std lockguards in order, you'd end up with the potential for deadlocks due to lifetime issues. In C++17, we wanted to extend std lockguard to make it variadic and support locking multiple mutexes. When combined with class template argument deduction, this made correctly locking multiple mutexes a lot easier and more elegant. This would be backward compatible. Before C++17, you were able to instantiate a std lockguard with a single template parameter. And with this change, you'd still be able to do that, and it would have the same semantics. But This would change how std lockguard was mangled on some platforms, which would be an ABI break. Let's take a look at how std lockguard with a single template argument would be name mangled with GCC or Clang under the Atanium C++ ABI, both with and without this change. As you can see, the mangling for std lockguard of std mutex would be slightly different if std lockguard was changed to take a variadic template parameter instead of just one template parameter. We didn't realize the implications of this change at first. We voted it into the committee draft of C++ 17. It was only during the final phase of C++ 17's evolution that the committee realized that this would be an ABI break. So, sadly, we decided we couldn't make this change to std lockguard. Instead, we introduced std scoped lock, a variadic form of std lockguard. This is a good example of how we can often get around ABI roadblocks to evolution by introducing an improved facility under a new name. The major downside is that this leaves us with two versions of the same thing that we have to maintain. During the C++ 17 cycle, it was proposed that we add a new overload of std system errors message virtual function. The new overload would not allocate and would be no accept. You'd provide it with a buffer to fill the message. This was a completely additive change. The new virtual function would be non-pure, so it would be backward compatible. Existing classes that derive from std system error would not have to implement this new overload. However, as we've discussed, making any change to a std virtual table, even an additive change, will break the ABI of that type. So sadly, we were unable to pursue this change. ABI constrains not only C++ standard library evolution, it also constrains quality of implementation. Std mutex was introduced in C++ 11. In C++ 17, we introduced std shared mutex, a more complex form which supports multiple levels of access. In theory, std mutex should be as efficient or more efficient than std shared mutex, as std mutex is simpler. However, unintuitively, MSVC's std shared mutex is about 2 times faster than its std mutex. Why? Well, std mutex is older and it has to support an older ABI and older platforms, including Windows XP. So it must be implemented in terms of the older and slower Windows Critical Section API instead of the newer SRW lock interface, which can acquire a lock with a single CAS on the fast path. MSVC's std shared mutex is only faster by virtue of being newer and not having to support an older ABI. Not only is MSVC's std mutex slower than std shared mutex, it's also 10 times the size of std shared mutex. That is suffering, my friends. That is the embodiment of tragedy. This could be fixed. Std mutex could be implemented using the same faster primitive as std shared mutex, but that would be an ABI break for MSVC. I want to impress upon you that while the C++ standard library is good at stability, it is bad at fixing mistakes. So, what do we do about this? I think many people think this is a zero-sum game. Stability versus velocity. We must pick one at the cost of the other. Which do we pick? Stability or velocity? Which is our priority? This is the wrong mindset to have. This is a false dichotomy. Stability versus velocity is a myth. We can't just make a binary choice here. That's just picking one group of users at the cost of another group of users. Today, all major implementations guarantee some degree of long-term stability. They do that because that's what a lot of their users want. It is unrealistic to think we will stop caring about stability. We have some users who need stability, but we have other users who don't need stability who are having to pay for it. This violates one of C++'s tenets. You don't have to pay for what you don't use. While the C++ committee has not taken a clear stance on stability and velocity, this isn't something we can fix with policy alone. We need technical solutions that will allow us to make breaking changes to the C++ standard library while still providing stability to users who need it. Let's take a look at some of our options. In C++ 11, we introduced inline namespaces, which were supposed to help address this problem. Members of an inline namespace are treated as if they are members of the enclosing namespace in many situations. They can also be used explicitly by their full name if needed. For example, if I have an inline namespace cxxnn in stud, and that inline namespace contains a definition of string, stud string will resolve to stud cxxnn string. I can use it in my code as stud string. However, for purposes of name mangling in ODR, it's still actually stud cxxnn string. This becomes useful when we are dealing with code compiled with different C++ language dialects or compiler versions. In C++11 mode, my standard library can use one inline namespace, cxx11. In C++23 mode, it can use a different inline namespace, cxx23. Then, if I build code that uses stud string with different C++ language dialects, each component will really be using a different type. In source code, it appears that I'm just using stud string, but under the hood, I'm using two different versions of stud string that are distinct entities with distinct names. I can't accidentally mix them. If I try to pass a stud cxx23 string to a function that only takes stud cxx11 strings, I'll get a build time error because no overload of that function exists. In theory, if I needed to call a function that takes a stud cxx11 string from C++23, I could explicitly create that type of string using its full name, stud cxx11 string. In practice, this isn't possible today. While some standard library implementations support using different stud ABI versions and different translation units in isolation, none of them support using multiple stud ABI versions in the same translation unit. Standard library implementations don't maintain a separate copy of stud facilities for each different language dialect or ABI version. Instead, they have one set of headers and source files which are parameterized on a macro that sets the ABI version and inline namespace. Enabling multiple versions of stud facilities in a single translation unit might be possible, but it would be quite challenging to implement, and it may make C++ standard library codebases harder to maintain. Inline namespaces can't diagnose all our ABI problems. What if I've got a function that just returns a stud string, but doesn't take any stud entities as parameters? Unfortunately, inline namespaces can't catch this. The return type of a function isn't a part of its mangled name, because you don't need to know it for overload resolution. So a function that returns a stud string will mangle the same when compiled with stud cxx11 string, as it will when used from a translation unit that expects a stud cxx23 string. This will lead to a silent violation of C++'s one definition rule, the ODR. Your code will blow up at runtime. Likewise, inline namespaces don't help us detect mixed ABI usage when you embed stud things in your types. The data members of your types affect their layout and size, but do not affect how they are mangled. So if I compile code that uses a type with a stud cxx11 string member and pass it to a translation unit that expects that member to be a stud cxx23 string, I'll get a silent ODR violation and bad things will occur. Inline namespaces are not as great at detecting ABI breaks as we might hope. However, some C++ standard library implementations put everything in stud as an inline namespace, which makes it more likely that some usage of stud things in your code base will trigger detection of ABI breaks, even if it's not the usage that will actually cause the breakage. But inline namespaces don't solve the problem of mixing different ABI versions of stud facilities. All they do is diagnose the problem. They don't give you a way to make an older stud string and a newer stud string interoperate. Clang, GCC, and the Itanium C++ ABI support an extension that makes inline namespaces a bit more useful, Abi Tags. They can be applied to a variable, type, function, or inline namespace declaration via attributes. ABI tags are viral and recursive. If something with an ABI tag appears in a function's signature, then the function gets an ABI tag itself. ABI tags get added to the name mangling of functions and types. Let's go back to our earlier example of a function that just returns a std string. Inline namespaces don't help here because the return type doesn't influence the mangled name of functions. With ABI tags, since our function used a std string, which has an ABI tag, our function will have an ABI tag, which will be added to its mangled name. This means that the ODR violation will be detected. Someone trying to call the function with a newer std string ABI will fail to link because there's no version of our function compiled with the newer ABI tag. However, ABI tags aren't a perfect solution. They aren't propagated from data members to their classes. They also aren't propagated to a function that uses something with an ABI tag internally, but not in its interface. ABI tags don't do anything to address interoperability between ABI versions. They just diagnose problems. A few years ago, the committee started exploring the idea of std2, introducing new versions of std features which are not compatible but may be interoperable with their older counterparts. This first came up when we were deciding where to put the new range-based overloads of our algorithms, which today are in std ranges. We thought that perhaps instead they should go into std2, and we should start a broader effort to overhaul our existing facilities and add new versions in std2. There was a lot of excitement around this idea at first, but we quickly realized this would actually cause a lot of problems. Would everything that's in std today have a std2 form? If so, would they be interoperable with their std counterparts? If not, how would you know which things are in std2 and which things are in std? Would you have to write separate overloads for things that are in both std and std2? There's a whole class of solutions to stability that end up being morally equivalent to std2. A std2 approach is any solution that involves duplicating and maintaining multiple generations of the same facilities. For example, introducing a variadic std scoped lock because we can't change std lockguard. While std2 approaches often have merit and are often the best option available, they have downsides. With the techniques that we have today, these approaches have a big maintenance burden and complicate the C++ standard library interface by introducing multiple things under different names. So, let's take a look at a new technique that would make this approach more viable. What if we codified interface versioning into the C++ type system in core language? There's a very exciting proposal that does just that. With interfaces, when writing something, you can specialize parts of it for different versions. For example, imagine we were designing a std point facility. The first version of this type would go into C++23, so we put everything in the type in a C++23 interface block. The argument to an interface block is an interface tag. The C++ standard library would define standard interface tags, like std cxx23, but you could also define and use your own interface tags. In the C++23 version of std_point, we have 3 data members. If we need to add another data member in C++26, we can do that using an interface block. We can also remove or change members. If we wanted to make the point only contain an x and a y in C++26, we could do that too by having one top-level interface block for the members in C++23 and another top-level interface block for the members in C++26. We've also got 3 member functions in the C++23 version of our point type, each of which just returns a data member. In the C++26 version of the type, we add a 4th member function that retrieves the new data member that we added. Interfaces would be part of the type system. Interface std cxx23 point and interface std cxx26 point would be 2 distinct types. With this proposal, writing and maintaining multiple versions of library features would be substantially cleaner. Interfaces also support forward compatibility. They can be used to generate resilient types that can accept newer versions. If I have a function that takes an interface CXX23 std string, there's no cost to that. That takes a std string of a known fixed interface version. That interface will only support C++23 std strings. But I could also write a function that takes a resilient std string. An interface CXX23 plus std string is forward compatible, and interfaces that take such a string can accept newer std string versions. There's some cost to that resiliency, of course. Under the hood, some sort of type erasing wrapper will be generated by the compiler. You wouldn't be able to inline member functions of std string into a resilient function. There would probably be other restrictions too regarding introspecting the layout and size of resilient types. But you would only pay for those costs if you need resiliency. With interfaces, we can do more than just diagnose version mismatches. We can support multiple versions and forward compatibility. I believe the interfaces proposal, or something similar, is essential to the future of the C++ standard library. But until we have better tools in the language for supporting both stability and velocity, we must live with the realities we have today. Until we learn to change things after we ship them, the C++ standard library should only contain things that are unlikely to need many changes. Today, the C++ standard library is good at stability and bad at fixing mistakes. The C++ standard library shouldn't innovate. The C++ community should innovate. Once innovation has been proven in the field, then the C++ standard library should standardize that existing practice. Anything that goes into the C++ standard library must stand the test of time. Will we be happy with it in 10 years? In 20 years? We must avoid premature standardization in evolving fields. If there's substantial active research, or the best practices change every few years, it's not ready for the standard. Consider our unordered containers, which we standardized in C++11. They're all node-based, but today we know that in many cases, flat unordered containers have superior performance. Even when compared against other node-based unordered containers that conform to the same semantics, including iterator invalidation, implementations of std containers do not put up favorable results. Just by changing the way we hash keys, we could substantially increase the performance of our unordered containers. But we can't apply the knowledge we have today to our standard unordered containers because of stability. We need to see field experience before we can standardize. Field experience has three components. Implementation experience is the experience we get implementing a proposed design. Are we confident the design can be implemented? Has someone built a prototype implementation? Has someone built a production implementation? Can it be built on all platforms? Has someone tested it? Ideally, we're looking for experience building a new implementation from scratch based on the specification for multiple platforms in a production environment, ideally a C++ standard library codebase. We also want experience using implementations of the proposed design, usage experience. Have we clearly identified what the intended use cases are? Are we confident the facility is useful and usable for all of those use cases? Have people used it? Have they used it in production? Have we clearly identified what is not supported? Do we understand all the possible limitations and pitfalls? Are there examples? And we want experience evolving and maintaining the proposed design. Deployment experience is implementation experience and usage experience over time. Have we had implementation experience and usage experience over a long enough period of time to understand the maintenance burdens of the facility? Do we have experience making changes and updates to the facility? That's what I want to see in a proposal: implementation experience, usage experience, and deployment experience. If we can't change a feature after it ships, then we should ship only what is needed, because we may be unable to fix any mistakes we make. But on the other hand, if we can't change a feature after it ships, then we should ship as much as possible because we may be unable to add more later. These two forces conflict and often lead to delays in C++ evolution. Incrementalism is key to C++ standard library evolution. We're bad at changing things, but we're good at extending them. I often ask, if we don't include this in the initial release of the feature, is it a breaking change to add it later? If the answer is yes, then if we want that functionality, we must include it in the initial release of the feature. If the answer is no, then we must consider whether the feature has any value without the functionality in question. If the feature is useless without that functionality, then it must be included in the initial release. Otherwise, we could, and probably should, exclude the feature from the initial release and add it later. Until we learn to change things after we ship them, the C++ standard library should only contain things that are unlikely to need many changes. I want to emphasize that this position is conditional. I want us to learn how to change things after we ship them. Now, let's discuss my philosophy about what kinds of features should go into the C++ standard library. I believe that the C++ standard library should only contain facilities that cannot live anywhere else, things that must be there by necessity. As we've discussed, adding features to the C++ standard library takes a lot of effort and has many constraints. Many things would be better suited to a different home. Therefore, we should only put things into the C++ standard library if there's no other home that could work for them. I think there's 3 criteria that qualify. First, there's facilities that require language support from the compiler for correct or optimal implementation. For example, type traits. Most of them have to be implemented in terms of a compiler built-in. Or std stack trace, which needs to be implemented using platform-specific APIs or compiler built-ins. Or std tuple element. This doesn't require any special compiler support to implement, but it's a customization point that the compiler uses to determine how to decompose your types for structured bindings. You could implement std memcopy without compiler support, but many compilers have a faster built-in memcopy that the compiler backend can recognize and reason about. The next criterion is portability. Facilities that provide portable abstractions of platform-specific behavior and interfaces. For example, std chrono. Every different platform, Windows, Linux, Mac, GPUs, embedded environments, has clocks and different APIs for querying them. Std chrono gives us a single abstraction over all of those platform APIs that will work anywhere. Or std atomic, which abstracts portability across hardware and operating systems. It's also fundamentally tied to the compiler and thus requires language support. Std sort is another example. There's a bunch of different algorithms for implementing sort, all with different trade-offs. The right trade-offs differ from platform to platform and domain to domain. Or std numeric limits, which abstracts and exposes details of your hardware and compiler's math environment. The final criterion is vocabulary, facilities that need a common definition for interoperability across the C++ ecosystem. There's 2 types of vocabulary. The first is interface vocabulary, the concepts, types, and operations that commonly appear in C++ interfaces. We need common definitions of these so that different code bases can interoperate. For example, we need to have ranges and iterators in the C++ standard library because everyone's libraries are going to be parameterized on ranges and iterators. If a user uses my library and your library, they shouldn't have to deal with 2 different but morally equivalent definitions of input range. Likewise, it's a pain for users if every library defines its own string type and they have to deal with all of them. That's why we have std string view in the C++ standard library, so that there's one common string abstraction that can appear in interfaces. Everyone can still have their own string types for their libraries if they want, but by making them convertible to a std string view, they can ensure that their string types will work with everyone else's code. Interface vocabulary includes things like core concepts, fundamental containers and views, algorithms, because they are part of the interface of our containers and views, Instead of having every algorithm be a member on each container class, we parameterize the algorithms in terms of iterators and ranges and separate them from any one container, making them generic and more powerful. Another example would be std_format. This is an interesting one because it's a function and doesn't appear in interfaces itself. But it provides ways for us to define formatters for our own types. Having std_format in the standard means we have one common and standard way to define those customizations across code bases. If your library defines a custom formatter for your types, my library can use them with std_format. There's also tooling vocabulary, facilities that tools will want to recognize and treat specially. For example, by having containers, iterators, and ranges in the standard library, MSVC and GDB can build special support for them into their debuggers so that their contents are easily accessible and visible when debugging. Kling's static thread safety analysis wants to be able to recognize concurrency primitives like std_mutex or std_atomic. So that's my premise. The necessity thesis. The C++ standard library should only contain facilities that can't live elsewhere. Facilities that either need language support, provide portability, or serve as vocabulary. The C++ standard library should do less, better. Now with that said, what features do I think qualify? What does belong in the C++ standard library? I'll tell you 4 broad areas that I think we should focus on in the 2020s. First, asynchrony and parallelism. We live in an increasingly asynchronous and parallel world, and it's time for C++ to catch up. We need a common vocabulary for expressing asynchronous work and data, vocabulary that can be used across the C++ ecosystem. That's what C++ executors, senders, and receivers will provide us, and hopefully we'll get them in C++ 23. These asynchronous and parallel primitives will set the groundwork for many of the other things we want to build in the future. For example, modern input and output facilities. Today, performant I/O is done asynchronously. So when we add things like networking or modern file I/O to the C++ standard library, they'll be asynchronous, building on top of executors. A lot of that input and output will be text. It's long past time for the C++ standard library to have proper facilities for processing text. We need first-class support for Unicode as part of our vocabulary. Finally, 2 of the major language features we'll be driving in the 2020s, metaprogramming and reflection, will require substantial standard library support. We'll need to continue expanding the scope of constexpr in the C++ standard library so that you can use nearly the entire standard library at compile time. That's my vision for the C++ standard library in the next decade. Asynchrony and parallelism, I/O, text processing, and metaprogramming and reflection. Some disagree with my view on what belongs in the C++ standard library. They feel that the C++ standard library should expand in scope to contain anything that is useful to C++ programmers. I dislike this criteria because it lacks focus. I hate to be the person that says we can't have nice things, but nice is not sufficient motivation for standardization. We've talked in great detail about the burdens of being in std, and we haven't even covered all of them. In light of these burdens, what would motivate people to try and get so many things into the C++ standard library, especially when those facilities would probably work just as well as a popular library on GitHub or in Boost? I think it comes down to default availability. There is great value in being part of a monolithic distribution. It means that your feature is everywhere that a C++ toolchain can be found. Some believe the best way to achieve widespread availability of their facility is to try to get it into the international standard for C++. I think that is indicative of some fundamental problems in the C++ ecosystem. Is there a popular C++ library that has the facility you want to add to the C++ standard library? If there's not, is there really sufficient field experience to justify putting the facility into the C++ standard library? Remember, we standardize existing practice. If there are popular libraries that implement the facility that you want to standardize, why aren't those libraries good enough? Sometimes people tell me that the problem is that their company or project only lets them use things that are in the C++ standard library, or that they have to do paperwork to use anything else. I sympathize with this problem, I really do, but it is not the C++ standard library's problem to solve. Standardization is not a substitute for culture change. Okay, maybe you've got a specific reason that the facility should go into the C++ standard library. Maybe it needs language support, or it abstracts portability, or it needs to be part of the vocabulary. Can you live with making no breaking changes to that facility for the next 20 years? If so, then is it worth at least 5x the effort and time that it would take to just put your facility on GitHub? If the answer is yes, then okay, let's talk. Your facility may belong in the C++ standard library. Often, people tell me that the reason that they're hesitant to use other C++ libraries is that managing dependencies in C++ is hard. Well, have you tried a C++ package manager? Some great C++ package managers have appeared in the past few years. The two with the largest market share are VC Package and Conan, and they work on most platforms. I hadn't tried a C++ package manager until recently. I was working with a code base that used VC Package, and I was pleasantly surprised by how easy and simple it was to use. Nothing like what I was used to from 5 or 10 years ago. The C++ standard library is not a package manager. The problem isn't that C++ has no package manager. The problem is that there are too many. So can C++ standardize package management? Honestly, I don't know. It is far outside of the realm of anything that we've ever tried to do in the past. As C++ committee members, package management may be out of our scope. But as leaders of the C++ community, it is our duty and responsibility to act. Using external libraries in C++ should be an order of magnitude easier than it is today. This should be the primary goal for C++ in the next decade. So what would we even standardize? C++ package metadata formats? Could we standardize a way for describing how to package projects? Could we standardize a way to describe dependencies? This seems like a good area to start. What about a standard C++ package manager? That is a lot more challenging. Remember, universality is key to C++'s success. It would be hard to build a package manager that works for most C++ users. I think we'd do better to focus on enabling C++ projects to interact with existing packaging ecosystems in a standard, system-agnostic way. A centralized C++ package repository? Well, I think we'd need a standard C++ package manager for that. And as I said, I'm not sure about that. But perhaps we could make a central registry of package names and metadata to avoid name clashes and ensure consistency across ecosystems. What about a standard C++ build system? Well, we already have one. CMake has over 50% market share. Every toolchain, IDE, and package manager supports it. You want a standard C++ build system? You got one. It's called CMake. Resistance is futile. Just use CMake. Until recently, there was great diversity in the build systems that C++ projects used. Fortunately, at least each project usually just had one or two build systems. With the advent of modern C++ package managers, if you want to make your code widely available, you've got to do some work to describe your project to each different package manager. I would like a world where the C++ ecosystem continues to coalesce around our de facto standard build system, CMake. I'd also like to have a single way for projects to describe how they should be packaged. If everything uses CMake to build, perhaps this makes it a bit easier. I think we're going to continue having multiple packaging systems, both C++ specific ones and system package managers. That's a feature, not a bug. There is room for diversity in the distribution and management of code artifacts and repositories, as there's many trade-offs there. However, I think it would be good to have some sort of central package name registry so that we could at least have some consistency in how we request packages by name and version. Given that the different packaging systems use different versioning mechanisms, it's not clear how viable this is, but I think it's worth exploring. I think there's one more option that we should explore. Today, we have the C++ standard library, which comes with your toolchain and works everywhere. However, putting things in the standard library often duplicates effort, and the standard library has many constraints on it, especially regarding stability. External libraries have only a single implementation and can have a narrower scope and intended user base, which makes them more flexible. Their major downside is that they must be acquired separately from your toolchain and aren't available by default. I would like to see a middle ground solution that combines the best of both options. C++ collections, a set of curated C++ libraries that optionally come with all major toolchains. But they'd only have a single code base instead of one for each different implementation. These libraries would have more flexible stability guarantees than the C++ standard library. Pre-C++ 11, the Boost C++ libraries fulfilled this role, although they did not come with your toolchain. Perhaps Boost has a role to play here in the future. But until then, until we learn to change things after we ship them, the C++ standard library should only contain things that are unlikely to need major changes. The era of big standard library is over. The C++ standard library should do less, better. It should only contain facilities that can't live elsewhere. Facilities that either need language support, provide portability, or serve as vocabulary. We must find a balance between stability and velocity. We need new tools, like interfaces, to make that happen. Using external libraries in C++ should be an order of magnitude easier than it is today. This should be the primary goal for C++ in the next decade. I want to thank all these excellent people who helped me prepare this talk. I also want to thank all of you for listening. The last year has been challenging for all of us. I'm glad that we've still found ways to come together as a community and talk about our favorite programming language. I hope to see all of you in Aspen at a future C++ Now.